In this video, we're going to be looking at rates of reaction, recapping the concepts that you will have looked at both GCSE and AS level. To start with, I'd like you to think about how you would determine the rate of cooking an egg. Now consider how you determine the rate of cooking popcorn, so those kernels popping into the white popcorn. And this should hopefully give you an idea about our rate of reaction. So our rate of reaction is the rate at which our reactants are used up. For example, the popcorn reaction where the kernels are used up in order to make the white popcorn, or the rate at which the products are made, so there your cooked egg being formed. And so we have two equations for our rate of reaction. They're both given in this box here, but we can consider it being the amount of product produced divided by the time taken, or the rate being the amount of reactants used up divided by the time taken. As reaction progresses, we get fewer reactants, so the red and the blue, and we get more products. So to start with, there are no products being produced, but by the end of the reaction, when the reaction is complete, it's 100% products. And from this, what we see is that our rate of reaction at the start is very high because we've got lots of reactants available to react, but by the end of the reaction, there aren't many reactants to react, and therefore our rate of reaction slows down. So we can see this when we look at the graph. So you'll notice it dips off towards the end, and that's because our amount of reactants has decreased as our reaction progresses. We can also use our graphs to get our rate of reaction. As you'll notice, our amount of product is on our y-axis and our time is on our x-axis. So we can calculate our rate of reaction by using the gradient of the graph. And what you'll notice is that the gradient, the steepness of that line, decreases as the reaction progresses. And so the gradient of these graphs gives us an indication as to how the rate of reaction is progressing. At a particular point, we can calculate the rate of reaction at that point by drawing a tangent to that point. So a straight line that runs alongside the graph at the same steepness as the graph line is at that point. We've also looked before at collision theory. So this states that in order for our reactions to take place, the particles need to be colliding with enough energy for our reaction to take place. And we've talked a lot about activation energy before, and that's our minimum energy that particles need to have before they can react. So the two parts of the collision theory is that the particles need to collide, and they must have an energy greater than the activation energy. So in order to increase our rate of reaction, we need to consider how we could increase our chances of the reaction. So here, looking at the collision factor and our activation energy factor. So anything that results in more frequent collisions is going to increase our rate. As more collisions, more chance that there are successful collisions. But also, if there is more energy, then those collisions are more likely to be successful. So there are 5 factors which increase our rate of reaction: increasing concentration of solutions, increasing pressure of gases. Now these two are very closely linked together, so we're going to talk about those together. Increasing our temperature, increasing surface area, and addition of a catalyst. So we're going to start off with our pressure and concentration factor. So both concentration and pressure are talking about amount of substance in a particular volume. So if we're increasing the concentration or increasing the pressure, we're saying that there are more particles in a given volume, and therefore you're going to have more collisions between those particles if there are more of them, and therefore your chances of a successful reaction between those particles is going to increase as more frequent collisions are occurring. Here is an example of our increase in temperature. So increasing temperature gives our particles more kinetic energy. So not only will they have more energy and therefore an energy greater than the activation energy, but also they're moving faster in their container, and therefore you're also going to be increasing the frequency of the collisions and therefore also increasing your rate of reaction. Increasing the surface area gives our reactants more opportunities to react with the other species. So in this image, the green species has various different surface areas, and our red reactant is able to react faster if there are more sites at which it could react with the green particles. Use of a catalyst decreases the activation energy needed, and so the energy at which your particles have been supplied is going to be closer to the activation energy, i.e. you don't need as high a temperature in your reaction because it's easier to reach that activation energy as it's lower. And remember, catalysts do this by providing an alternative pathway. We're going to look at that in a moment. In our reaction profiles, we have what's called a transition state, which is at the top of the peak. And this is where we've got bonds which have been partially made and bonds which have been partially broken as the reaction is happening. This is a very unstable substance, and due to that additional energy compared to either the reactants or the products. So it doesn't exist for very long, but it's a transition between the reactants and products before it goes to completion. This is an example of adsorption and desorption from a catalyst. So here we've got a platinum catalyst surface, and we're showing that our SO2 and O2 molecules are adsorbed onto the surface. They then react on that surface, and the products are then desorbed from that surface. These images are showing you the structure of zeolite catalysts, and what you can see here is that it's a very open structure. So it's got holes going through the structure, and that means that not only can reactants go onto the surface from the outside, but also through the holes they've then got an additional surface area. So that open porous structure increases the surface area, and just like with increasing rate of reactions by our reactants having larger surface area, having a catalyst with a larger surface area is also going to improve the rate of reaction, as it provides more sites for adsorption onto the surface to happen. Okay, so with our Maxwell-Boltzmann distribution, it's a graph showing our number of molecules on our y-axis against our energy along our x-axis. When we have our Maxwell-Boltzmann distribution, it always starts at 0, as there are no molecules with an energy of 0. However, as our energy increases, our number of molecules at those specific energies increases, and eventually it tails off. Now notice this line never goes back down to 0, but what we get from this graph is a number of molecules above a specific energy, for example, our activation energy. So here we can look at the number of molecules that have an energy greater than our activation energy, and that's the shaded area underneath the curve. When we introduce a catalyst, we're lowering our activation energy, so I'm just going to use a C to show that it's a catalyst, and therefore our number of molecules that have an energy greater than the catalyst has increased as we've got a larger shaded area underneath that curve. We can also consider how temperature changes this. So if this is our initial temperature, T1, if we were to increase our temperature, we already know that that means we're going to have more molecules with an energy greater than the activation energy, and this means that our shaded area must increase. We also know though it still has to start at 0, and so in order for the area to increase above the activation energy, then our curve rises shallower, but the peak then falls later. Sometimes you'll often see it lower, but the point is that we now have all of this that is greater than our activation energy, greater than our activation energy when a catalyst is used, due to that larger shaded area. So our peak moves to the right, and it never crosses, so it only crosses the T1 line once. And that's because if it was to then go back down again, you'd then be cutting off that area. So this area extends, and this line won't go below that line, so it only crosses there. Both have to start at 0, curve increases for higher temperature, so T2 here is greater than T1. That rise is shallower because the peak comes later at a higher energy.